This is Jeff Hamrick at the University of San Francisco's MSFA program. This is a quick Stata demonstration on the sample autocorrelation function plots and the sample partial autocorrelation function plots in Stata. What I've uploaded into Stata here is a set of information from Yahoo Finance, the price of IBM stock for approximately the past decade. I'm going to focus here on volume as being the time series of interest. Now you'll recall that with any time series data set in Stata, you have to explicitly declare the time variable. These dates that are in this data set are actually pretty good candidates for that time series variable, but unfortunately these dates are strings, and we would need to manipulate them to get them into a format that Stata would be willing to accept as a time series variable. So because I'm going to be content to regard for this exercise these dates as being equally spaced apart in time, I'm just going to go on ahead and declare, as we're often going to do in this class, a kind of dummy time variable. So I'm going to call a variable time, and I'll index it by n. If we take a look at this guy, all I'm doing is I'm acknowledging that this volume of shares of IBM stock is what was traded on day number 1, which happens to be the 3rd of January 2000, and so on and so forth. Okay, so I then need to tell Stata, as you'll recall, that my time series variable is in fact time, and that's Stata's acknowledgement of that fact. And now I can operate Stata's various time series related functionality on this data set, now that there is a variable by which Stata can understand this data set as a time series data set. So the most simple instantiation of a function that will compute for you and kind of draw for you the sample autocorrelation function and the sample partial autocorrelation function is going to be choregram. So the syntax as usual when you don't want lots of bells and whistles or filters is pretty simple. You just use choregram or corelograms, and I'm going to act on the volume information. So I'll press OK here. There's a fair amount of data in the data set, so it takes a little while for this stuff to draw for us. Let's talk about this output really quickly. So we have here a certain number of lags that Stata defaults to showing us, 1 through 31. More are available. These are the values of the autocorrelation function, and these are the values of the partial autocorrelation function. This Q right here is the Box-Jung test statistic associated with lag 1. This Q is the Box-Jung test statistic associated with lag 1 and lag 2, because the Box-Jung test statistic is cumulative, and that's why you'll see that this Q only increases in magnitude as the number of lags increases. Of course, even for this very first lag right here, this Q, which is a chi-squared test statistic, in this case with 1 degree of freedom, is associated with a very small p-value. So, of course, you'll recall with me that the Box-Jung test statistic is connected with the autocorrelation function. That was the Box-Jung test is a test that we learned to test whether or not the autocorrelation function up to a certain number of lags is statistically distinguishable from 0. So this information here connects with the autocorrelation function values. When I take a look at these quick sketches of the autocorrelation function and the partial autocorrelation function, I immediately notice the following. It's possible, I guess, that the autocorrelation function is dying at a geometric rate. I'm not really happy about the rate of decay down here. And it's possible that the partial autocorrelation has a sharp cutoff after 3 lags. That might suggest that a good Box-Jenkins time series model to use in this context would be an autoregressive model of maybe order 3. Okay? Because you'll remember that it's pure MA processes that have ACFs that cut off sharply, and it's pure AR processes that have partial autocorrelation functions that cut off sharply. That is, if the other function is dying down at a geometrically slow rate, which might be the case here. It's a little ambiguous, I'll acknowledge. These plots, while nice, they're kind of quick and dirty, are not the only way you can draw the sample autocorrelation function in Stata. Another route would be to use AC for autocorrelation function and ask that to be drawn for volume. I'm not using any of the bells and whistles here. This is another representation now of the autocorrelation function. As you can see, it dies off slowly, probably not at a geometrically fast rate. Probably we need to be a little bit careful in using our diagnostic tools here. These bounds right here are the 95% confidence intervals that you could roughly use to establish whether or not the autocorrelation function is statistically distinguishable from zero. I think it's not here. All of these values of the ACF are outside of these confidence interval bounds. So I think it's very fair to say that the autocorrelation function is not equal to zero. We are not dealing here with a white noise. The way you can get the partial autocorrelation function is with PAC. So let's take a look at that. And here we're kind of seeing the same picture that we were seeing in the sketch before. I see the first lag right here is a very high value, and then a couple of other higher values, and then maybe a couple more that are statistically distinguishable from zero, but then definitely the thing seems to cut off after some point. Once again, the gray shaded region is the 95% confidence interval, the asymptotic 95% confidence interval for a partial autocorrelation function that is truly equal to zero. So I think here we've got some evidence that the PACF is non-zero for the first few lags, which again might suggest that an AR model might be appropriate to model volume on IBM stock. So this is how you can use Stata to generate the ACF, the sample ACF, and the sample PACF. Let me know if you have any questions, and good luck with the homework.